So question number 5. So we have a fixed beam and it is subjected to complete UDL, and the span length is length L, and the uniform distributed load W per unit length. That is the intensity of loading in the beam. Okay. So we have to find collapse load. So what is the collapse load? So the question is find out collapse load. So we can use any method. So what is the collapse load? That means at the failure, what is the maximum load this beam can take before before the failure? That is what the collapse load means. So we have two theorems. We can use any one, or we can use both. So first we will solve by using static method. Okay. So all these questions are very similar. You just have to understand it. Okay, the procedure. The first static method, or or lower bound theorem. Okay, static method, or also known as lower bound theorem. So in this theorem we have to know the moment diagram. Okay, so at least we should know the shape of the moment diagram. Simple case, we will be knowing the standard formula also. I can make use of that. So for the fixed beam, we know that this will be the moment diagram. It will be, so this is the your bending moment diagram. So we'll have a rectangular diagram, that is your fixed end moment, and it is by free moment. Okay, so this will be so this will be, if you draw your bending moment diagram, usual moment diagram. Let us draw that bending moment diagram at elastic state. That means what is this value, what is this value, and what is this value. So this, what is the equation for this one? So what is the value of this moment at the fixed end?
WL square by 12.
So this is WL square by 12, and this is also WL square by 12, because symmetric loading. So both the fixed end moments are equal. So WL square by 12, and this, what is this length? What is this value total?
WL square by 8.
So WL square by 8. This is WL square by 8. So this is the moment diagram in the elastic state. So now can you tell me where is the maximum moment in this fixed beam? What is the maximum moment? Where will be the maximum moment? So your maximum moment will be here at the mid span. What is the net moment? Only this much. This is the net moment. That will be WL square by 8 minus WL square by 12. Okay. How much will be that? 1 by 8 minus 1 by
1 by
12.
24.
Okay. Yeah. So this will be only WL square by 24. So this value, this net moment, yeah. So this will be WL square by 24. But at the support we have WL square by 12. So that means your maximum moment is WL square by 12. Sorry, yeah, 12 at the fixed end. So this moment will be something less than half that. It is just half. Okay, because in this case, so I think, yeah, in this case, if you see this loading case, fixed beam with a pointer at the center, this moment and this moment both are equal. This is also PL by 8. It is also PL by 8. All these moments are equal. These three moments are equal value, equal in magnitude. Okay, here it is not equal. Um, so that means, so initially, so for the, it is a fixed beam. So your static indeterminacy is, degree of static indeterminacy will be 4 minus 2. It is equal to 2. Okay, that means for the failure we need ds plus 1, this many plastic hinges. This 3 plastic hinges is required. Then only this structure will fail. Okay, so 3 plastic hinges will required. So the what we have to find the collapse load. We have to find out the collapse load. So what we have to do is, this is our given beam, and we will be keep on increasing the load. So the load is, and keep on increasing up to failure. So corresponding load is your collapse load. So as you increase the load, as you apply the load, it will start bending. There will be deflection. So initially the deflection will be less, and the load is keep on increasing, and final all this, as you increase the load, all this moment at the fixed end and the midspan, everywhere the moment is keep on increasing. So where will be the moment will reach plastic moment first? At which location your moment will reach your plastic moment MB? So at which point it will reach MB value first in this beam? So you can, that is the use of the moment diagram. That is why we are drawing the moment diagram. So at which location your your moment will reach MB?
Sir, can you again repeat the question?
At which point your moment will be reaching MB, limiting value, plastic moment. So as you increase the load everywhere, your
At
moment.
midpoint.
At which point?
At midpoint. L by 2.
How? Why L by 2? L by here this peak moment is already less. This moment is more than that. As you increase the load everywhere, the moment value will be keep on increasing.
Okay.
So this value is just half of this value. At the fixed end, we have the moment value is always higher at the fixed end. That is what this equation W L square by 12. It is W L square by 24. And if you are increasing the W, and finally this the moment at the fixed end will be reaching the plastic moment first. That section will reach this condition. Your stress will be reaching this yield condition, because everywhere the moment is increasing, corresponding stress is increasing. Finally, first the plastic hinge will be forming at the two support. Okay, first plastic hinge will be forming at the only at the two support, because in this case this value, this moment and the moment at the fixed end is two times your moment at the midspan. Okay, whenever this is reaching MB, this midsection the moment will be something less than your plastic moment. That may be partially elastic and partially plastic, that condition. But these two plastic hinges are not enough to have the failure. With the two plastic hinges, your structure will not fail, because still it can take some more load. So then we'll increase the load further, and after that, if we increase the load further, these two section cannot take any more moment. So all the moment will be distributed to the other sections, and finally a stage will come, and your midspan moment also will be reaching your MB plastic moment, fully plasticized this condition. So that stage will be called, this is the your collapse stage. This is the collapse stage, or will be called mechanism. Okay, this is the collapse stage. So then only your structure will have failure. So two hinges are not sufficient to cause the failure of this beam, because it is a indeterminate of degree 2. So we need three plastic hinges. So that does not mean that all the three plastic hinges will form simultaneously. It will not be like that. So initially we have some loading, and then keep on increase the loading, and first the plastic hinge will be forming wherever your moment is maximum. So in this beam, your moment is maximum at the two fixed support. So the first two hinges will be forming simultaneously at the two fixed support A and B. So these two hinges will form simultaneously. But with these two hinges, your structure will not collapse. So what we are analyzing, we are finding out the collapse load. So we have to we have to load up to the collapse load. Then only we can get that collapse load. So the two hinges are not sufficient. We need the third hinge. So I will increase the further load, and the next moment will be reaching MB. And what is the next maximum moment section? That is your midspan. So finally a stage will come. Third hinge will be forming, and once the hinge has formed, this part will be just it will deform like a rigid bar. It will be just like a rigid bar. There will not be any bending. It will be just linear, straight. So this is the stage we are analyzing our structure. So we have to draw the moment diagram at this stage, at this collapse stage, or you can say at the plastic state or plastic state. Okay. So that moment diagram only we have to draw. So our moment diagram will be like this. So now what is the moment at the two fixed support? MB. What is the moment at the midspan? That is also MB. Okay, because that is the mechanism has been formed, because now we have three hinge, and we are analyzing your structure at that stage. Okay, so all the three location your moment will be MB. Okay, that means what is this value? It is MB. This moment is MB. This also MB. So we are drawing your bending moment diagram at plastic state. At plastic state. Plastic state means your structure is about to collapse, about to fail. Then what is this value? Can you tell me what is this value? What is the net moment at the midspan now at the plastic state? This one also will be MB. Okay, because all the three locations we have the plastic heat. This one also MB. So now we know that it is MB anyway. And what is this total height? That is W L square by 8. W L square by 8. So now we can make use of that condition. This total height is equal to W L square by 8. So at the collapse stage, so I am then replacing my loading with collapse load. So W L square by 8, which is equal to MB. Total height is in terms of MB, you can say MB plus MB. So 2 MB. Okay, so finally you can say that this collapse load is equal to 16 times 16 times MB by L square. Okay, 16 times MB by L square. So that is how you have to find out your your collapse load. It is a collapse load in terms of kilonewton per meter. Suppose if you want to find your collapse load in kilonewton, that is just WC into L, 16 MP by your length span. Okay, let us take capital L. So this is 16 MP by L. Okay, so this is the because we are analyzing our beam at the plastic state, so we have to take all the three peak moment. We have to take this, that is equal to MB. Okay, so that does not mean that all the three hinges will be forming simultaneously. It will not be like that. The first two hinges will be forming as the two support, then we will increase the loading further, then only our third hinge will be forming. Okay, but in the other question, in this question you can check the moment, all the three moments are same value. Okay, that means all the three plastic hinges will be forming simultaneously. All the three in this structure, all the three plastic hinges will be forming simultaneously. Okay, but for the failure we need three plastic hinges, so we have to load up to that up to the three plastic hinges. So up to that time we have to load our beam. Okay, then only your then only it will collapse. Okay, so this is the procedure you have to do in the case of static method. So similarly now we can solve by using kinematic method. Let us check what is the answer coming from the kinematic method. Kinematic or upper bound theorem. So usually the kinematic method is much simpler than static method. When you go for continuous beam or little complex structure, you have to follow the kinematic method. Okay, because you can follow any method uh, most of the time. So unless it is not specified in the question, you can use any method. Okay, you can use both the methods or you can use any one. So in kinematic method, we know this is the mechanism. We have to we have to assume a mechanism, and to form the mechanism, we need three plastic hinges. So your mechanism will be like this. So we have the beam, the one hinge, second hinge, and finally the third hinge. So now I have one, two, and three plastic hinges. Okay, and this hinge will be forming at the center. Okay, because wherever these are the three locations we have the maximum moment. So so there only we have to assign your hinge. So now we can find this is the angle theta, this is the angle, it is a rotation theta, and because this hinge will be at the middle, at the midspan. Okay, so this angle also will be theta, this angle also will be theta. So now this is the hinge, so we have MB, and here also we have MB, and here we have MP, MP. Okay, so now we have the loading. Yes, we have the uniformly distributed load also there. So we have the loading in the beam. So the load also acting in the beam. So now we can apply the kinematic theorem. That is, we have to equate the external work done equal to internal work done. Okay, and external work done, that is equal to your load into, this is my load into displacement, load into corresponding displacement. So that is, we have the loading is W. So what is the displacement? So W into, suppose if I have only one point load is acting, maybe like this, and I have some displacement delta there. So external work done is this load plus PC into delta. Okay, but because here I have only one load is acting, but in this case this load is there throughout the your beam, entire length of your beam we have the loading. So W into this delta into all the delta means all this displacement you have to take. So this one you have to multiply with each and every point, like, okay. So that means if you have a UDL in the entire span, so how will you get the external work done? We can this finally what is this term? All this delta if you take, that is finally the area of this triangle. That is why for the UDL we can find out the work done is equal to the intensity of UDL into area of this deformed shape. Okay, let us take this value, the displacement at the at your midspan, that is delta. So your work done will be W into area of this triangle finally, that is half into delta into, let us say, L. This is the external work done. Okay. And how will you get the internal work done? Internal work done you can get. So internal work done is, you have to at this plastic hinge location we have the moment MB. MB you multiply with corresponding slope. Moment into slope, that is the internal work done or strain energy. Internal work done is nothing but your strain energy actually. So this plastic hinge location, it is having some moment MB and it is rotating. It is having some rotation theta. So we can get the strain energy or internal work done, that is your MB into corresponding rotation theta. So how will you get that? It is MB here. So I can write MB multiply with this rotation at that point, MB into theta, plus here we have MB theta, MB into theta two times, MB theta here and MB theta here. So that is your MB into total rotation is actually theta plus theta. Okay, and here MB into theta. So here always at this plastic hinge we have to show your moment MB, we have to take the two side. Okay, that is why MB theta plus MB theta. Okay, so finally this will be 4 times MB theta. And what is the relation between your theta and this is the collapse load, your intensity UDL. Okay, and what is the relation between theta and delta? You can write theta is equal to delta by L by 2. So that is 2 times delta by L. That will be your the value of theta. Okay, so this
Sir,
uh,
sir, during writing, while writing the internal work done, sir,
hmm,
the MP to theta and another MP into theta, sir, these two will be in opposite direction, na, sir.
no,
One at the
that
one right side.
it will be like this. Let us explain that. I have explained this part already. So anyway, so we have some loading. So this is the state. So here we have what is the angle theta. How will you get theta? From the horizontal? Maybe we can say this horizontal and this angle is theta. Here the theta means the change in slope is theta, and here also we have theta. But here what is the total rotation between two members? So this is one tangent and it is another tangent. So the total angle is this much. This is the change in angle between two members. This is the first and this is second member. So this total angle will be, let us take this is theta 1, it is theta 2. So this one also will be theta 1. It is theta 2. Okay, finally this total angle will be theta 1 plus theta 2. Okay, so finally, so this is the internal work done. So mp into theta here, mp into theta here, and here you can see physically, you can see the at that junction we have a rotation, so it cannot be mp into 0. That is anyway logically wrong. So you can see that at that section we have some internal, you have some plastic moment mp, and there is a rotation theta. So that is the internal work done, mp into theta plus mp into theta. So finally we have 4 mp theta, and now we can take this condition. So you can substitute theta equal to 2 delta by L. So it will become 4 times mb, 4 times mb, theta is 2 delta by L. So your external work done, that is WC delta L by 2. Okay, so your collapse load WC 4 into 2 8, 8 into 2 16 mp by L square. It is in terms of kilonewton meter. This is the collapse load. So or you can write in terms of kilonewton, that is capital WC, that is 16 mp by L. So again this all these questions you will get same value in the upper bound and lower bound theorem. So this is the collapse load 16 mp by L square in terms of kilonewton per meter, or in terms of kilonewton total load, this W into L. So that value is 16 mp by L. So maybe you can compare with your fixed simply supported beam with UDL. So the collapse load is 8 mp by L, or 8 mp by L square, and for this fixed beam, for the same loading, we have the load carrying capacity has become 2 times doubled. Its collapse load is 8 mp by L. It was for simply supported beam with UDL, and here we have 2 times 16 mp by L, because that is why, because here we have a fixed support, so it can take more load. So this is your the collapse load. Okay, so any doubt in this? Anybody have any doubt? Okay, so you have to understand clearly this one, you have to take mp if you are using the static theorem, because we are looking at this stage. If for the failure we should have 3 hinge, and where will that hinge will form, that depends on your moment diagram. You should know at least the shape of the moment diagram. You should be able to say that where will be the peak moment, these two location and this location. This is a 3 location, you may have peak moment. So all the 3 location hinge will form first. Once it reach that stage, then you can say that this beam will be going to fail. It is a failure condition because we have 3 plastic hinge. So we can go to next question. That is question number 5. Next, I think we have to question number 7. So I will solve. So next we will take this question number 7. Okay. So again you have to find what is the collapse load. Find out the collapse load PC. So we have a propped cantilever beam, and here what is the static indeterminacy? Degree of static indeterminacy. Here for vertical load I have a 2 reaction here, 1 and 2 and 3. Yeah, so 3 minus 2. So your static indeterminacy is 1. So that means we need ds plus 1. So we need 2 plastic hinges for the failure. Okay, 2 plastic hinges for the failure. So up to that point we can load. 2 plastic hinges required, okay, to form the failure, or to form the mechanism, or to have the failure. So we have to that is our condition for this beam. So I think you can the moment diagram always will help you, so that you can identify where will be your peak moment will be happening, so that you can understand from the moment diagram. At least you should know the moment diagram. Okay, even though if you don't know the values, it's fine. You can apply the kinematic theorem. This will be your fixed end moment, like at the simply support moment is 0, and at the fixed end we will be having maximum. Okay, so your moment diagram will be, so this we have discussed in the fixed beam analysis. Moment diagram, how to draw the moment diagram by parts. So this is the This is your fixed end moment diagram, and for this point load we have moment diagram is something like this. So at the midspan we'll have some value and it will be something like this. So that means maybe so let us draw your moment diagram at collapse. Okay, so means first we can compare these values. You know the standard result. These values we can compare it. Okay, what is this value? One thing is clear from this moment diagram. So this is one peak value you can expect at the fixed support, and another peak value may be in the span somewhere. Okay, in the span here can expect maximum maybe here. Okay, so these are the two critical section. You can expect a maximum value. So whichever is maximum, this one you can compare the values from the moment diagram, and let us assume the fixed end is maximum moment. That means you will keep on increase the load. First hinge will be forming at the fixed support. So then one hinge is not sufficient to have the failure. We need two plastic hinges. Okay, and then we will increase. We'll go beyond that. We'll increase. We'll further. We'll do the loading. Then your second hinge will be forming at this location. So finally, two hinge will be forming. One is at the fixed end, and the next one will be at the your wherever your load is acting. Your point load is acting. Okay. So that is why we have to see finally at the collapse stage it will be like this. So we have the beam and I have some loading at the center or somewhere. So first hinge is forming here, and you keep on increase the load further, your next hinge will be forming here. Okay, this is your collapse load PC. So that is why this at this location your moment will be MP. This location also your bending moment will be MP. Okay, that is your limiting value plastic moment capacity of your beam section. So that is why your bending moment at the collapse stage, this value will be equal to MP, and this one also will be equal to MB. Okay, and if it is MB and this is L by 2, this distance is L by 2, this distance is L by 2. Okay, this is your L by 2. That means what will be this value? We can find out from similar triangle. This one will be MB by 2. This height will be MB by 2 because it is MB. So I am using this triangle. So I can use the similar triangle MB by L, that is equal to this height by L by 2. So finally this will be MB by 2. Okay, and now I know what is this total height. What is this total height? That is your PL by 4. PL by 4, because it is your moment diagram, sagging moment diagram in the simply supported beam with load at the midspan. So this total height is PL by 4. So and this height in terms of MB, that is MB plus MB by 2. So I can write 3 MB by 2, 3 MB by 2, that is equal to 3 MB by 2 means MB plus MB by 2. Okay, so I think I will write like that, MB plus MB by 2, MB plus MB by 2, which is equal to your PCL by 4. So we are applying your lower bound theorem. Okay, so this implies we can say 3 times MB by 2, which is equal to PCL by 4. So we can find your collapse load PC, that is equal to 4 into 3, 12 by 2, 6. 6 times MB L by 4. 6 times MB by 6 MBL by 4. Okay, that is our collapse load. And now we can apply your upper bound theorem. So upper bound theorem is based on the mechanism. So the mechanism will be like this. So we need two plastic hinges. So this anyway plastic hinge will not form. It is a physical hinge. It is a hinge support. Okay, so there is no question of plastic hinge at this point because there is no moment at all. It is a physical hinge. It is already a hinge. So there is no question of plastic hinge is forming at this simply support. But one plastic hinge will be forming at the fixed support, and the next plastic hinge will be forming your load point. Wherever your load is acting, the concentrated load, you will have a peak moment definitely, and that point your moment will be your plastic hinge will be forming. So this is equal to your collapse load, and this is my mechanism, and here I have MB, and here I have angle theta, and because this hinge is at the center, this angle and this angle, everything will be theta. MB, it is MB. The plastic hinge your moment is MB, and these two angles are theta. This angle also theta. So now we can apply your external work done. External work done is equal to internal work done. Okay. So our external work done is PC into load into displacement at that point. So let us take this point. Your deflection is delta. So PC into delta, which is equal to, that is your external work done. PC your collapse load into your corresponding displacement, that is the work done. PC into delta, and internal work done is your MP into theta, moment into rotation. So at this section, MP into theta, MP into theta plus, when you come to this section, so your moment is your internal work done, that is your strain energy, that is your uh, moment into plastic moment into your corresponding rotation theta. So MB theta plus MB theta. So finally you will have, it is equal to 3 times MB theta, and we have the relation between theta and delta, that is theta is equal to 2 times delta by L, 2 times delta by L. For small angle theta, theta is equal to delta by tan theta, delta by L by 2. That is what this equation. So I can write 3 times of 3 MP into theta is equal to 2 delta by L. So this is equal to 6 MB by L. Delta will get cancelled. This is my collapse load. 6 MB by L. So upper bound and lower bound theorem both are giving the same result. So a collapse load for this case, that is your that is a 6 MB by L. 6 MB by L. That is the case of a propped cantilever. Okay, I think we have done that for fixed beam already. Let me take that fixed beam constant load 8 MB by L. Okay. So now you have to, all these standard results are very important. You have to remember that also. Let us compare that, the three case for the same loading. So where is the question? I could not get that. Question number, not this, 7, 5 and 7. Number 7. Yeah. So this collapse load is 6 MB by L. Okay. The first case, let us take simply supported beam. How to remember this? That is what I am explaining. So we have derived all those things. So first I have a simply supported beam, your concentrated load at the center. Let us say W. Second, I am just one support is making fixed, another one is simply support. It is an overhanging beam. Sorry, propped cantilever L by 2, L by 2. Here also L by 2, L by 2. And third case, we have the fixed beam. Both support, this support also made it fixed, and it is your it is your loading, and L by 2 and L by 2. So what is the collapse load here? That is equal to 4 MB by L. We have derived 4 MB by L, and this collapse load is equal to 6 MB by L. Okay, and this collapse load equal to 8 times MB by L. Okay, so the simply supported beam will be having very less capacity, 4 MB by L, and proper cantilever beam, it is more than your simply supported beam, 6 MB by L. And when you come to the fixed beam, it can carry much more load. It can carry, load carry capacity will be very high. So your collapse load will be higher than these two cases, that is 8 times MB by L. And where MB is the your plastic moment capacity of the cross section. So MB is a constant, because MB is finally, if you know the material properties, your yield strength multiply with your plastic section modulus. Your ZP also, if you given a cross section, your ZP is a constant value. You can find A by 2 into Y1 bar plus Y2 bar. So MB is a constant all the case, provided your cross section is dimensional same, material is same. Okay, but the collapse load will be, it is higher for this fixed beam. It depends on your support conditions. If you make it very rigid beam, like very fixed beam to support, you are making it fixed, it can take more load before failure. That is what this equation is telling us. Okay, 8 MB by L, 4 MB, 6 MB by L, like that. So this is the question number 7. So this is how we have to find out the plastic moment. 6 MB by L. So if you, do you have any doubt in this, you can ask me. Question number 7. Okay. And the next we'll go to question number 8. I will not solve it. Same question. We have a fixed beam. Sorry, we have a probe cantilever beam. Okay, and the loading is not at the center, and you can solve it easily. It is not difficult. Same procedure. We need two plastic hinges. So two plastic hinges are required to form the mechanism. Okay, let us apply the kinematic theorem. So this will be the first one plastic hinge. Okay, and second one will be at the point of action of your load. Second plastic hinge will be forming maybe somewhere here, and this is my load PC, and this length is A, this length is B, and here this is theta 1. Okay, and this is also theta 1, and this angle will not be theta 1, it will be theta 2, something different. This is also theta 2, and this is a plastic hinge, and we have plastic moment MB here. It is another plastic hinge. So this is one first, it is second hinge. So we need two plastic hinges to form a mechanism. Okay, then only your beam will have failure. So up to that point you have to load, and that is your corresponding collapse load. So I can apply the external work done is PC into delta, which is equal, delta is a displacement at this section, this maximum displacement delta, that is equal to, what is the internal work done, that is MB theta 1, MP into theta 1 plus MB into theta 1 again plus MB into theta 2. Okay, so now we have to write theta 1, theta 2 and delta. All the three you have to write in terms of any one unknowns. Either you can represent all the three in terms of theta 1 or in theta 2 or in terms of delta. So let us write theta 1 and theta 2 in terms of delta. That may be simple. Theta 1 is equal to your delta. This is my this is my delta here. This is your delta. So theta 1 equal to delta by A. Delta by A. And theta 2 is equal to delta by B. Because we are all taking these theta all small angles, so I can, tan theta is equal to or approximately equal to theta, so theta 2 is equal to delta by B. So I can substitute your theta 1 and theta 2 in terms of delta in this equation, and then you have to just solve it. You can simplify this easily, and you will get your collapse load PC will be, you will get this equation. This will be your final result, MB by AB multiply with L plus B. Maybe write like this, L plus B. So final result will be L plus B divided by AB into MB. So you can solve your own and you can compare. This will be your collapse load. Okay, the procedure is simple, same as the just question number 7. There is no change. Okay, you can easily solve it. Okay, so that is the kinematic theorem, always simple. You can always use the upper bound theorem. Okay, you can always use the upper bound theorem to solve it. Okay, so that is question number 8. So now we will go to question number 9. So this is actually, I would say, it is very important question. Many times it will be asking in exam, and also this result also is going to use very useful when you are solving your continuous beam or frame. Sometimes this result we can directly use. Propped cantilever beam subjected to UDL throughout the length. Okay, so that will be that question we will discuss. So this question we will solve it completely with all the steps, because this is an important question. So we will see this. So probe cantilever beam again, loading is UDL. So find out your collapse load. That is the question. Let us take the intensity of the load is W. Find out the collapse load. Find out the collapse load. The WC. Okay. and here we know that static indeterminacy equal to 1. Okay, so number of hinges, the number of hinges required to form a mechanism. Okay, mechanism is the failure condition, that is your ds plus 1, that means 2. So you need two plastic hinges to have the failure, two plastic hinges for the failure. So we all of us know in the moment diagram, the shape at least you will have the moment diagram will be like this. So maximum moment at the fixed support, 0 at the simply support, and then we'll have your parabolic, your UDL, the free moment diagram, that will be a parabola. So parabola. So this is your okay. This is your moment diagram. Okay, it is your, this will be your, let us say, plastic moment diagram, plastic bending moment diagram. So in this case, where will be the maximum moment? One is, we can say, at the one maximum moment you can expect at the support. So when you are in the plastic state, this will be your MB. Okay, and where will be your another peak? If you check your bending moment at the midspan, let us say midspan may be somewhere here. Okay, you will get some value. But from this, because this is a finally your net moment diagram is only this much. This is your negative moment. It is my positive moment. This part is going to get cancelled. This triangular part. Okay. So this part will not be there. Means let me draw that. The green color. I will take a green color. So this part is not there in your moment diagram. This is just got cancelled, right? Positive and negative. So your net moment diagram is only this white color. This part negative moment. This is your sagging moment. So one maximum moment you can expect at the support. Okay, and if you see the midspan, your moment is something, some I have this much moment, right? But can you say that this will be maximum or it will be maximum somewhere else? If you go maybe towards this side, you may get something more than that, because this is a triangle and your net value, your maximum sagging moment you will not get at the center in this loading case. Okay, maximum sagging moment will not be at the center, it will be somewhere else. We have to locate that section, and that section moment we have to assign MP to solve it. So we have to find out where will be that point in your beam. Okay, let us take that point. This section is the maximum. Let us assume that this is a section where we have the maximum moment, and then this will be your MP. Okay, this will be your MP. So because this diagram will go like this, so we have a, this is your free moment, fixed moment, and center I have same value. Then we'll have like this. Okay, so at the center you will not get maximum, your maximum may come somewhere here, some other section. Okay, so that you can understand. If you draw in a proper scale, you can understand that. Then we will derive that where will be the location, we'll derive that, then we can check whether it will be center or it will be at somewhere else. We will see that. Okay, so this moment max, let us take this section is let us take this point is C, this point is A, and this point is B. Okay, so that means we need two plastic hinges. So your plastic hinges forms at A and C. So wherever you can wherever you have a peak moment, that point only your plastic hinge will be forming first. Okay, and for the failure we need only two plastic hinge. That is why we are taking only two locations, because it is a beam with indeterminacy 1. So here you can say that plastic hinges form at A and C. Okay, A and C. Okay, so this is my So one moment is here, maximum is one is here, it is MB. So another one is this one MB. Okay. So let us take the point is A, this point is C, and this is B. And let us take this distance is x meter, x from your support B. It is x meter from your support B. Okay. So this is MB, and then I can find at this point what is this height. It is MB, total is L. So I can apply the similar triangle and I can find this value. This height will be, it will be nothing but MB into x by L. MB into x by L. Okay. So from this triangle, you can say MB divided by length L, which is equal to this height. Let us say the height is y by x. So what is this height then? MB by L into x. That is what this MB into x by L. Okay, MB by L into x. This height is MB x by L, and this section because this section has to be, it should be maximum moment. So this we have taken MB. We don't know what is value x. We have to solve it. So but in terms of x, I can write this value MB into x by L. Then what is this total height? What is this total value? So we are applying the lower bound theorem. What is this total height? How will you find this total height? So we are applying the lower bound theorem only. So for that we got this MB. This is MB into x by L something. And how will you get this total height in terms of W and X? In terms of this W and X. So maybe how will you get this total height? How will you get that? So what is this? It is a moment diagram for your simply supported beam. So I can easily write this value at this section. So we will take a simply supported beam. We'll have the simply supported beam. So what is this parabola? It is your bending moment diagram for the simply supported beam with UDL. Okay. So this is my loading, and this reaction will be WL by 2. Okay. And we are taking a section here x. This distance is x meter, and this total height, that is nothing but your bending moment at this section, okay, at the section C, bending moment at the section C, that is what this. So we can see that mxx, and here I am calling MC for the section I am calling, this is section C. So that moment is WL by 2 reaction into x, WL by 2 into x, that is the sagging moment, minus this UDL intensity WX square by 2. Okay, that is this value. So it is nothing but your MC. So now we can do as usual this MC, that is this value WL by 2. Okay, so we can write this one, this height in terms of MB. What is the height? MB plus this height is MB into x by L. MB plus MB into x by L, total height, that is equal to MC, that is equal to WL by 2 into x, WL by 2 into x minus WX square by 2. Okay, and from here we can simplify. You can write MB equal to, okay, not you can write MB into from here you have to simplify it further. So anybody, is it clear? Anybody have doubt up to this? I will clarify if you have any doubt. So is it clear up to this point? Any doubt you have? Okay. So now I can write this is MP into 1 plus x by L. I'm just simplifying it. MB into 1 plus x by L, which is equal to WL by 2. I'm just taking the common. WL by 2 into x minus, it will be x square by L. Okay, it is a simplification. So now I can write MB equal to, so MB equal to WL by 2. It's a lengthy procedure, but the end result you have to remember finally. So that is a important part. So this is x minus x square by L, x minus x square by L. So we have to multiply this one. This part is okay. Small letter, capital, both are same. Let me write small letter only. Okay. So this is x plus L by L. Okay. So this I am taking into right side, so right hand side. So this will become L by x plus L by x plus L. Okay. So now we can again this part we can have to expand like WL by 2. So this is Lx minus x square, Lx minus x square by L, multiply with L by x by L. So these two L will get cancelled. Okay, these two L will get cancelled. So we'll get it is equal to WL by 2, WL by 2 into Lx minus x square divided by x plus L. That is my MB. Okay, and finally this MB, this ordinate should be maximum. That was our, this ordinate should be maximum. This MB should be maximum. For that, what is the value x? That is what we are trying to find out. So in this moment diagram, at the center, at the midspan, this net moment may not be maximum. Okay, because if you go towards this side, you may get a maximum value somewhere there. That is the section at the point at this section C. That section is at a distance x meter from your support B. So now our condition is this MB should be maximum. This section, the moment should be maximum. MB should be maximum. So corresponding moment we can find out. So we will do the first derivative test like dou MB by dou x. I can take the derivative of MB. So we can take the derivative with respect to x, that is equal to 0. That is what we'll do the next step. So finally MB equal to this one. MB equal to, we got MB that is equal to WL by 2 into Lx minus x square, Lx minus x square by x plus L. Okay. So now we'll apply this condition dou MB, right here. So dou MB by dou x, it should be 0. So we'll take the derivative with respect to x equate to 0. Okay, because we have to solve x, and for that at this section your this moment should be maximum. It is MB actually here. So that is why we are taking the derivative. Right now we got expression for MB in terms of x. So we are taking the derivative with respect to x, that you can equate to 0. So now only mathematics you have to take the derivative d by dx of u by v. That formula you have to use. So I can find this is my w. Okay, this is my w. So WL by 2 is a constant. We'll keep it outside. And you have to take the denominator part x plus you have to apply that formula derivative d by dx of something like this, u by v. You have the equation. So d by dx, so you take the derivative of the denominator, that is 1 into your numerator Lx minus x square. Okay, so minus, take the derivative of your numerator, that is L minus 2x multiply with denominator x plus L, that is your derivative, divided by x plus L the whole square. This must be equal to 0, right? This must be equal to 0. So that means this product is anyway it is not equal to 0, so this quantity must be 0. That is a condition you are going to get from here. This is this one into this one should be 0. That means this term must be 0. This term must be 0. That means your numerator must be equal to 0. Finally, you will get the condition is Lx minus x square minus L minus 2x into x plus L, which is equal to 0. So from here you have to simplify it further. So this is Lx minus x square, so which is equal to this quantity. Uh, so L into x, so that is Lx plus L square minus 2x square minus 2xl. Okay, so I think I'm correct. So from here you can take everything like minus x square minus 2x square, so it will become, if I take everything to this side, or it was already in this side, so I think you can expand this one and you can simplify it. Okay, it is just simplification only. You will get a quadratic equation finally: x square plus 2xl minus L square equal to 0. So now we can solve for x by using, again, we can find the root of your quadratic equation, that is your x equal to, so minus b plus or minus, so minus b, that is 2l minus 2l plus or minus square root of b square minus 4ac by 2a. So I think you know that equation, 2b square minus 4ac 1 into, so by 2 times a, 2 times 1. So this is equal to minus 2l plus or minus, it is 4l square plus 4l square. So square root of 8l square. Square root of 8l square, that means 2 root to l by 2. Okay. So which is equal to minus l plus or minus root to l. Right? Minus l plus or minus root to l. So that means your x is equal to minus l plus root to l. So minus L root 2 is 1.41, so minus L plus 1.41 for L. That is the first root, minus L plus root 2 L, or second root is minus L minus root 2 L. So which is equal to this quantity minus L plus minus plus 1.41 for L root 2. So that you will get 0.41 for L, 0.414 times L. For second root is coming minus 2.414 L. This is a 2 root for x. And what is your finally, what is this x? X is nothing but this distance. The total length is L. Total length is L, and x is this distance, and that means this cannot be a solution. This cannot be a solution for our problem. This cannot be a solution. It is not possible. That means for x, finally your x is equal to minus, sorry, 4.414 times length. Okay. That means in our beam, this is our beam, we have a prop cantilever and we have the loading UDL. So first one moment is there, maximum, that is your fixed end moment at the fixed support MB, and another section having the maximum moment will be somewhere here at a distance of 4.414 L times from this support, from this simply support. So these are the okay, so so that means your one hinge may form here and second hinge may be somewhere here. Okay, but that will not be at the center. Okay, so this will be your distance 0.414 L. So this one you have to remember, it is very important. Okay, this is very important thing you have to remember. So this will be the first plastic hinge. Second plastic hinge will be somewhere at this section. It will not be at the L by 2. It will not be at 0.5 L. Right, it will not be at the midspan. So but it will be somewhere here near to the midspan, but 0.414 L from this simply support, not from the fixed support. Okay, from this is zero point 0.6. This is the second class hinge location actually. Okay, so this is the value for x. So now because we are following this procedure, now I can directly find the collapse load maybe from here itself. So either you can use this equation, your MB equal to WL by 2 into Lx minus x square uh, by x plus L. In this equation, let me call this equation number 1. It is my MB, this one. From here MB plus MB into x by L, that is equal to this equation, and once you simplify it, you got the expression for MB. MB into W, MB is equal to WL by 2 into Lx minus x square by x plus L. So now we got the value of x equal to 0.414. So now we can substitute this value of x in equation number 1. Okay, so we got, so let me write it neatly here. This is my, so this is the moment diagram. So midspan. So this distance is your, it is equal to 0.414 times L, and where L is your total length. Okay, and substitute x equal to 0.414 L in equation number 1. Okay, so equation number 1 is equal to 1 is MB, that is equal to WL by 2. So WCL by 2 into Lx minus x square, Lx minus x square by L plus x. So which is equal to, we have to substitute WCL by 2 into L into x equal to 0.414 L minus x square, that is 0.414, this is x square divided by L plus x. Okay, L plus 0.414 L. Okay, so this one you have to simplify. I think you can do that. So what will be this value? Let me solve it. So this is coming WC into L by 2, and this total is coming this total ratio. Okay, this one is so L square you can take it common, and one L will be from here. So finally only L will be coming. One L will get cancelled. Okay, so this is 0.414 minus 0.414 square by 1.41 square. So I don't know, I'm getting this value 17157. Okay, so MB. So now I can write the collapse load from this here, that is equal to 2 MB, 2 MB divided by 0.1757 L square. So what is this value? 2 by 0.17. Yes. So this is coming 11.656656 MB by L square. That is the final result, which is this one you have to remember. So for this beam, this is my intensity of load. The collapse load WC, kilonewton per meter. Okay, that will be equal to 11.656 times MB by L square. This is very useful result. You have to remember this. Okay, so this is for the probe cantilever beam. Your collapse load will be 11.656 MB by L square, And if you want to draw the collapse mechanism, it will be like this. So your first one hinge will be here, and second hinge may be here, like this. So 1, 2. So this distance, what is this distance? That is not L by 2, it is 0.414 L. Okay. For which loading case, you should remember that loading is UDL. If it is a point load, wherever the point load is acting, that section you can take it. Okay, that section will have maximum moment. Hinge will be there only. But for the UDL, your hinge will not be at the center. It will be at a distance of 0.414 L from your support, from your simply support. Okay, so that is all about this question. So if you have any doubt in this question, you please ask me. Okay, any doubt in this question? So this one also you can compare. You take a simply supported beam UDL, you take a propped cantilever beam UDL, and you take a uh, fixed beam and UDL. What is a collapse load? For simply supported beam with UDL, your value was 8 MB by L, and for propped cantilever it is more than 8, it is 11.65, and for the fixed beam it is maybe 16 MB by L. Okay, like that we can see the difference. Like that you can compare like this. You take 3 beams, take UDL and write down all the formulas, and you compare your result. You will find an increasing trend. Your simply supported beam will have a least value collapse load, and then you will have propped cantilever, and then you will have fixed beam. Okay, so is it this is a lengthy because we have to derive with x value of x, because we cannot take its center, that is wrong. So that you can understand from the moment diagram only. From the moment diagram, if you draw, if you draw to some scale, you will find that at the center this ordinate will not be maximum. It will maximum at somewhere else, just near to that, not that much far, but zero point 0.9. This is around some zero point 0.9 distance. zero point 0.4. We are getting 0.41 now, so it is 0.5 minus zero point 0.4. There is a small gap. So if you have any doubt, you can ask me in this question. Question number 9. Question number 9 again. Any doubt? Next we will take question number 10. So it is a typical question, maybe like gate examination, you can expect question like this. Okay. Question number 10. So here we have a cantilever beam, and but cross section is varying. So this part is MB. This part is maybe having the least dimensions are less, so moment capacity is MB. Here maybe your beam cross section may be larger, your moment definition may be higher, and your MB value also higher. It is a plastic moment capacity. It depends on the cross section. Okay, because sigma y into ZP. So if you have a larger section, your ZP value will be higher. So correspondingly, your MB value also will be higher. Okay, that is what given in this question. Okay, so here first let us find out your static indeterminacy. Static indeterminacy R, that is 0. It is a statically determinate. Okay, statically determinate beam. So for the failure, we need R plus 1 number of hinges, which is equal to 1 hinge. So we need 1 plus a hinge, then it will form a mechanism. 1 plus a hinge is required to form a mechanism. Okay, so the question is same, we have to find the collapse load. We find out the collapse load for this beam. Find out the collapse load for this beam. Okay, so we need only one plastic hinge. With the formation of one plastic hinge, it will form a mechanism, and that is indicating a collapse. Okay, collapse stage. Okay, but here my question is, how many number of number of mechanism? How many mechanisms are possible in this case? So how will you get the number of mechanism? Anyone? How will you get the number of mechanism? How will you find out that?
The number of mechanism is equals to degree of indeterminacy plus 1.
No, that is not number of mechanism. That is the number of plastic hinges. So I'm asking how many mechanisms are possible in a structure. How will you find out that? The number of plastic hinge and number of mechanisms are different. We have seen beam mechanism, square mechanism, like that. In this beam, how many mechanisms? Means there is a for at least how will you find out the number of mechanisms? I have already discussed that previous classes. How will you get
And then
uh,
capital N minus R.
number of mechanism equal to, let us say, number of mechanism. N is equal to how much? That means you are not referring the previous notes or not. Okay, so anyway, the number of mechanisms are given by the number of possible plastic hinges. The number of the possible plastic hinges already we have discussed. So all these are important. It will be asking in a many examination. All this, even a frame can be given, and the question can be like how many mechanisms are possible. All can be a question. Okay, the number of possible plastic hinges we have to check. How many plastic hinges are possible? So minus your degree of indeterminacy. Okay, degree of indeterminacy. If I take degree of indeterminacy is R, then R. If you take something else, so this is your equation. Number of mechanisms you will get number of possible plastic hinges minus number of your degree of static indeterminacy. Okay. So here, how many what are the location where you can expect a plastic hinge in this case? How many possible locations? Hmm?
Support
Yeah, here maybe one is possible. Any other?
at the change of cross section.
Yeah. So here also it is possible. So we have, you can refer slide number. So refer. Let me show that one slide is there. You may have to refer that. So we have discussed that part also. Yeah, the number of possible location for the plastic hinge. It can be at the fixed end or at the rigid joint, internal support of a continuous beam, wherever you have the change of cross section, change of material, or point of maximum bending moment. Okay, all this can be the maybe slide number 59. I think I have explained this with an examples, drawings or something. So maybe it will be here. Okay, you can refer 49, 59 or 47. It is explained. So wherever you have the change of cross section, that is indicating your MB. Somewhere we have MB and another segment we have 2 MB. That means your cross section has changed. Okay. So at that junction, you can expect a plastic hinge may form there. Okay, plastic hinge may form there. So we have to consider that possibility also in the analysis. So that means in our question we have two possible plastic hinge locations. We have two possible plastic hinge locations. Refer slide number 47 or 59. Okay, for this point. Okay, so now the number of possible plastic hinges are two. Static indeterminacy, it is a determinate structure, so it is 0. So two plastic hinges are and two mechanisms are possible in this structure. So what are the two mechanisms? Two mechanism it is a failure mode. Okay, the first failure mode will be mechanism 1. Okay, mechanism 1. And for a mechanism at a time you need only one plastic hinge. I don't need two plastic hinge for, because it is a determinate structure. With the formation of only one plastic hinge, it will fail. It cannot take any more load after that. One possibility is the one hinge may form at the fixed support. Okay, at the fixed support one hinge may form. That is the first possibility. That means your structure may like this. We have a plastic hinge has been formed at the fixed support here. So then we have the loading here PC. So after that it will deform like a rigid body deformation. So this is the first mechanism, And what is second mechanism 2? So because here we got this number. Now two failure mechanisms will be is possible. So we have to analyze two mechanisms, and we have to find the collapse load from both these mechanisms. Then we have to check which one will be the governing failure. In which mode your beam is going to fail. Okay, so that will be the mechanism which give you the least value. That will be your governing mechanism. Okay, a second mechanism will be, so we have the fixed beam. Okay, a plastic hinge may form at this point, at this junction. Let us say this junction. Okay, so means once the hinge is formed, we have the loading here. It is going to deform like this. Okay, because of, you can say you have a cantilever beam and we have a hinge there. Once you apply the load, it is going to deform like this, rigid body deformation. This part will remain straight. Okay, once after up to that point, there maybe it is going like this. We have the structure. Okay, we have the we are applied the load. It will be initially, it will have bending. It will increase the deflection, increase the curvature. It will go like that, and finally a time will come, a hinge will forming here. So once hinge formed, after that it will just deform like this. It will just deform like this. This part will just remain horizontal. That is what we are drawing in the mechanism. So we are not drawing before MB how it was deforming. That is a different. That is for elastic analysis. Okay, that is not our discussion right now. So we have to analyze these two mechanism. Then I can find the collapse load from each of these mechanism. Then we have to take the least value for the collapse load. That will be the collapse load for your the given given structure. Okay. So now we will apply your kinematic theorem, upper bound theorem. So let us apply that. External work done is equal to internal work done. So let us take this is delta. Okay, and this angle is theta. And here we have what is your plastic moment at this joint? It is 2 MB. It is 2 MB. So your internal work done, that is equal to 2 MB times theta, which is equal to your external work done, that is the collapse load PC into delta. PC times delta. What is the relation between theta and delta? Simple. Theta is equal to delta by L. Delta by L. Okay. So let us take this is L by 2. This is L by 2. It is L by 2. So total like this L. Okay. So now we can substitute theta equal in terms of delta, and then we can just simplify it. So you will get the value of PC. This is L. So we can take this is equal to PC times, so delta equal to L into theta. So I'm just substituting delta in terms of theta. So L into theta. Theta will get cancelled. You will get PC equal to 2 times MB by L. 2 times MB by L. This is the collapse load for corresponding to this mechanism. Okay, let us say we got one value. Now let us check what is in this case. For this mechanism we have to do the same thing. We will apply the upper bound theorem. Your external work done, which is equal to internal work done. Okay, internal work done. So this is taken delta. Okay, the external work done is simple, PC load into the displacement delta, PC into delta, which is equal to, what is the value of MB at this junction? Actually here we have 2 MB, this is MB. Which value we have to take? And let us take this angle is theta. Okay, so your moment, your internal work done is value of plastic moment into theta. Okay, but here we at this junction, this part I have 2 MB larger cross section. This capacity of this section will be higher. This section having less capacity. You can say the half. Okay, this MB, it is having less capacity. It is having more capacity 2 MB, and this section will be having the capacity will be just half of this part. That means if you keep on increase the load, where your plastic hinge will be forming at this junction. At this junction, one side I have a weaker section, that is MB, and another section will have stronger section. At which section it will reach the plastic moment the value first? At which section it will reach the plastic state first? Weaker section or stronger section?
Weaker section.
Yeah, so that is why we have to take MB only. We cannot take 2 MB here. So this, while drawing, we are just drawing here L by 2 only. But really this plastic hinge is going to form in the weaker member. So that weaker member will reach the yield condition first. Okay. So your plastic hinge will be forming actually in this member only. So I will explain this in the case of frame in detail. Okay, with examples. So if you have a change of cross section, if you have the plastic hinge, if you have two value for MB, you have to take always the least value. You have to take always the least value. That means this would be MB. Okay, so this is final equation PC delta external work done, which is equal to MB into theta. So now we can again write your relation theta is equal to delta divided by what is this length? L by 2. So delta into L by 2. So that is equal to 2 times delta by L. That is my theta. So I can write MB. MB we multiply with theta, that is 2 delta by L. It is PC delta. So delta delta will get cancelled, and we can you will get PC is equal to 2 MB by L. Okay. So fortunately we are getting same value in this question, but it can be, suppose if it's 3 MB, it is 2 MB. So in that case you may get different value for collapse load in the two mechanisms. Okay, so that type of question we will be seeing later on, but in this question both this mechanism, both this case we are getting the same value of collapse load. Okay, so finally your collapse load is equal to 2 MB by L only, and if suppose this is 4 MB by L, it is MB by L. It is 4 MB by L and it is 2 MB by L. In that case we have to choose the collapse load is the least value. Okay, the meaning is, because if it is the least value, then this mechanism will be happening first. Your beam is going to fail in this way. The plastic hinge will be forming here, then your beam will be have failure. But in this case, both are having the same. That means both these plastic hinge will be forming simultaneously in the structure. That is the meaning. Okay. So both these plastic hinge will be forming simultaneously. Both this mechanism may happen simultaneously. Something like that you have to understand from this. So finally, your collapse load is how much? 2 MB by L only. There is no confusion because both these mechanisms are giving same value. If in case if we have two mechanisms, both are giving the different value, then you have to choose the least value. You have to choose the least value as the collapse load. Okay, because that mechanism will happen first. So we have to limit our capacity of your structure to that least value of load. Okay. So any doubt in this question, you can ask me. Question number 10. If you have any doubt, you can ask me. So in this question, there is no doubt, there is no confusion, because we are getting same value, so we can take any value, both are same. 2 MB by L. The answer is 2 MB by L. So many times this type of question used to ask in the gate examination. Simply supported beam or cantilever beam, where MB value will be different. Okay, usually the mistake may come at this junction. We may take 2 MB. If somebody take 2 MB, they will get this value is equal to 4 times MB by L. Okay, so that may lead to the mistakes sometimes. Okay, so we have to be careful with this point. So any doubt in this question? So we have 11, 12. So 11 and 12 we will solve it. These are simple questions. Okay, so next we will go to the continuous beam. So simply supported beam, prop cantilever beam, fixed beam. So everything we have completed. So we have to practice more questions so that you will understand. So that you will be able to solve the question very quickly. Okay, that is what I want to say. But we are stopping maybe the discussion on the simple beam. So maybe we will take one more questions. One or two questions are there in the, so we will solve it later. And next we'll move on to continuous beam. Okay. So continuous beam, we have to take it. Okay. So this is your next question number 11. Okay, so you have to find out the collapse load. Okay, all these questions are kept same. Find out the collapse load. Okay, find out your collapse load. So we have a three span continuous beam. All the spans are equal length L, and all the spans are having same moment capacity MB. That is what given in the question. Okay, so first let us find out degree of static indeterminacy. Okay, so that is let us take this is a hinge. This may be a roller. So anyway, there will not be any horizontal reaction because we have only vertical loading. So let us anyway. I have taken these all are rollers, and it is your hinge too. So where degree of static indeterminacy will be, you can say that if I count two here, 1, 2, then 3, 4, 5. So 5 minus 3. Okay. So you can also do in this way because the loading is only vertical. So anyway, this will not be there. So horizontal reaction I can eliminate. Finally, I will be having 1, 2, only vertical 3 and 4. So 4 minus, and I have eliminated one equilibrium equation also, 4 minus 2. So both the method you can get indeterminacy will be 2. Okay, indeterminacy will be 2 in this case. Okay, so now we will see number of possible mechanisms. The number of possible, the number of mechanisms. How many mechanisms are possible in this structure? Okay, the number of mechanisms, that is number of mechanism. I'm not using that symbol. I don't know what symbol I have given in that slide. N minus r some equation I given. I don't remember that exactly. Maybe small n. Okay, I don't confuse. Anyway, I'm taking capital N. The number of mechanisms. How many mechanisms possible? So you have to write the number of possible plastic hinges. The number of possible plastic hinges. Okay, the number of possible plastic hinges minus, because when you have a simple beam, and if we have uniform cross section MB, then there will be always only one mechanism will be possible. So always all these questions we can cross check. All these questions you can check how many mechanisms are possible. You can check that equation n minus r. You will get only one mechanism will be possible. Okay, that is why we did not find out how many mechanisms possible. We are not even checking here. Here there is no question of number of mechanisms. Only one mechanism will be possible. So this is the mechanism for the at the that is the mode of failure where you are going to have. So, but when you come to a continuous beam or beam with a change of cross section, in that case you may have to check more than one mechanism will be possible. You may have to check all the possible mechanisms like this. So definitely for a continuous beam on frame, you have to there will be uh, multiple mechanism may be possible. So you have to find out say procedure. First you have to find the degree of static indeterminacy. The next you have to find number of mechanisms possible in this structure. The number of mechanism means how many ways of how many modes of failure may be possible. After that we will find out what is the collapse load and which will be the failure mode, how your structure is going to fail. Okay, that is what we are doing the in the plastic analysis. So number of mechanisms are given by the number of possible plastic hinges in the structure minus your the static indeterminacy. Okay, degree of the static. So this one we already got 2. And can you tell me in this structure how many
Five.
plastic hinges are possible?
5.
Yes. So one 5 plastic hinges are possible. Okay. So because let me explain that if somebody could not uh, understand that. So let us draw the moment diagram. So again, drawing the moment diagram means in the plastic analysis, you should be able to draw the moment diagram at least the shape, so that you can say that where will be the maximum moment, so that I can tell you we can understand that okay those location plastic hinge may form. There is a possibility. So you don't have to remember the values of moment values, but you should able to draw the shape. So your moment diagram will be something like this. let us say this support is A, and this is B, and this is C, and it is D. Okay, and this may be like this. So it is a three span continuous beam. This is a fixed end moment, and then I can draw the free moment parabola UDL. So like this, right, and like this. This is the moment diagram. Okay, so this moment diagram must be clear because this is what we have discussed in the first two modules. First module, moment distribution, slope diffraction method. Okay, so this is my moment diagram. Okay, this is my moment diagram. So that means the peak location, where will be the peak moment you can expect. One is there, this is at the support we have a hogging moment, and this is also we have a peak moment, hogging moment. So at the two support, again you can refer the slide number 47 or 59. The possible plastic hinge I have written the support, internal support, it is a possible location because here we will have hogging moment, negative in the moment, so that may reach the plastic moment. And another way, somewhere in the span, it may not, it is again, it is very clear from the drawing, it will not be at the center, it may be something somewhere here, like your prop cantilever beam. So here one plastic hinge is possible, in this span one plastic hinge is possible, and again in this span at the mid span you will have a plastic hinge. Okay, so this is a point 1, it is another point 2 hogging moment, this is sagging moment, I have maximum moment, so 3, and here also we have sagging moment 4, and here also we have sagging moment 5. So that means 5 plastic hinges are possible. The possibilities are 5. 5 are possible, minus your static indeterminacy 2. So 5 minus 2, 3. So that means in this continuous beam, 3 span continuous beam, so your 3 number of mechanisms are possible. So what are the 3 mechanisms? Can you tell me what are those 3 mechanisms? What are the 3? We have studied beam mechanism, sway mechanism, combined mechanism, like that. So what are these 3 mechanisms? So this is actually, it is a number of independent, okay, number of independent mechanisms. So that means, so either this, if you have a 3 span continuous beam, so this there can be failure in the span AB, and next possibility there can be failure in the span BC. So we have to consider a beam mechanism in the span BC. Similarly, there can be a failure in the span CD. So even though only one span is having failure, so that entire structure will become unusable. So we have to consider that is like a failure of your entire structure only. Because even though a part of a structure has failed, we have to take that is a failure of your entire structure. Okay, so in this case, we have to check 3 mechanisms. That is, your span AB can be a failure, span BC there can be failure in the span BC, and the span CD can fail. Okay, so we have to take this individual case one by one. Then we have to find out the collapse load. And among these 3 failure, which is the least value, that will be the governing failure. That failure will happen first. And out from these 3 collapse load value we will get, from these 3 mechanism we will get 3 values for the collapse load. Out of these 3 we have to choose the least value. That will be the collapse load for your the given structure. Okay, the first, your span AB can fail. Okay, the span AB can fail, so that means it will be like this. Let me draw that. So anyway, it is not possible to complete by morning, so I will continue up to 12:15, I think, or can you let us complete this question, then we'll discuss. So the span AB, there can be failure in the span AB. Okay, that means like this, that we have 3 mechanisms. Okay, and the first case is like this, the mechanism 1. Mechanism 1, that means this is our beam ABCD. Okay, so ABCD, this is my beam. So A, B, C, D. Okay, your span AB will have failure. Okay, so now to have this failure in the span AB, so how many hinges are required? How many hinges? We can take like you can take this span AB like a you can treat like a prop cantilever only. This support B, there can be a hinge at the support, okay, and there can be hinge in between in the span. So this span AB we can take like this. This span AB is equivalent to this. So it is like you can treat like a prop cantilever B. And okay, so that means you for the, if you are taking only span AB, failure of span AB, you need only two plastic hinges. Okay, so it will be like this, like a prop cantilever. So you need only two hinges, and one hinge is possible at this support, and one hinge is possible somewhere here in the span. That means your failure of your span AB. That means something like this. So we will have a hinge here, and second hinge will be here. If two plastic hinges are formed, then there will be a failure in the span AB. Okay, and there is no failure in BC and CD. That is just standing. Okay, and this is here we have loading. This is the mechanism one. Okay, so this only two plastic hinges are required to have the failure in the span AB. And the second one is the next mechanism is in the failure can be in span BC. Okay, and that is your mechanism 2, like this. Okay, so A, B, C, and D. This is our loading. Okay, and here AB will be like this only. You can treat like a probe cantilever. Okay, so this is your AB. And when you come to BC, that will be similar to your fixed beam. Okay, for both the side we have the moment and we have the loading here. So there will be three plastic hinges are possible. So in the span BC, for the failure of the span BC, it will fail like a fixed beam. So we can have one hinge here, another hinge here, and third hinge will be at the mid span. Okay, because it is a just rectangle, and here we have parabola. So your maximum moment will be exactly at the center. It will be exactly at the center only. So for the failure for the span BC, we'll have three plastic hinges. Two will be at the support, and one will be at the mid span. This is the failure of your span BC. Okay, and span CD will be same as AB. There won't be any change, but that will be the mechanism 3. Mechanism 3. So we have your continuous beam. Okay, and this is the loading. So again CD, this is CD. So the span CD, there can be failure in the span CD. Okay, so again for the span CD, one hinge may be here and one hinge can be here. Only two hinges are required to have the failure. So it is like a probe cantilever. So one hinge will be here, one hinge will be here. So CD will be same as this case. So we have the loading CD. Okay, so now we have to find the corresponding collapse load. WC, intensity load, let us take WC, let's take WC. So these are the three mechanisms. There can be a failure in the span AB. To have the failure in the span AB, we need two plastic hinges. And for the failure in the span BC, we need three plastic hinges. 1, 2, 3. Can here again only 1, 2. So here again 1 2. Okay, so anyway MB is constant everywhere, so no worry. Okay, so yeah, so now how will you find the collapse load in this case? So again we can apply the kinematic theorem. If you want, we can apply the kinematic theorem. So this point, this angle, and this is W, this we can take it as delta maximum, then you can apply that. But finally what you will get, this hinge will not be at the center. If you look at this span, this maximum moment, this will not be at the center. Okay, this will not be at the center, but this will be like a probe cantilever beam only. This will be at 0.414 L. Okay, so everything is same, as you can solve it like a probe cantilever beam. This span you can solve it separate, but finally you will get same. Your collapse load will be whatever the result you have for the probe cantilever, same thing you can use, 656 11.656 MB by L square. Okay, this is the collapse load for the span AB. For correspond this mechanism, your collapse load is 11.656 MB by L. And if you take this span BC, you can solve it. It will be like a fixed beam only. In this case, it is much simple because this hinge will be at the midpoint only. Okay, this hinge will be at L by 2, and here this hinge will not be at L by 2. It will be 0.44 L. Okay, this will be at L by 2. If you want, you can solve it. This is MB theta plus MB 4 MB theta is equal to your external work done. So MB theta, 2 MB theta, MB theta. Okay, and we can solve it, and we have already solved this one for the fixed beam. So this will be your 16 MB by L square. If you write in, if you want to write in kilonewton per meter, then it is MB by L square. Okay, and this span, it is same as your span AB. There is no change. 414 L. Okay, it is a capital L, small l, both are same. Okay, and again here also we will get same value because all the beam, all the span having same length and same MB value. So all the this value and this value will be exactly same. So I can directly use the result. Okay, even though you derive it, you will get same value only. You have to derive this one. You have to do like a prop cantilever, and here you have to do like a simply, you have to do like a fixed beam. So this will be 11.656 MB by L square. So these are the three values we will get, 1, 2 and 3. Okay, so finally you have to write your collapse load will be, the collapse load will be the least. Okay, there is no space to write. Collapse load will be the least value. Finally we have to find the collapse load for this given continuous beam. So that is collapse load which is equal to 16 MB by L 11. So this is the least value. 1 and 3 are same. So the least value 11 point. This is the least value collapse load. Here collapse load I have written in terms of kilonewton per meter. Okay, intensity, in terms of intensity. So if you want to write in terms of kilonewton, it should be 11.656 MB by L. Okay, so this one actually we don't need to derive it. So I am directly taking the direct result from the standard loading case, previous simple problems. Okay, so this is how we have to solve the continuous beam. And in case if your MBs are different, let us say this is MB, it is 2 MB. So at that case, whenever you are using the joint, this hinge, this if you take a hinge there, let us say we have a question like this is MB, it is 2 MB. So whenever you are using the hinge at this point, you have to take the MB, the least value. Okay, sometimes this will be MB, this will be 1.5 MB. Okay, this is MB, it is 1.5 MB. So if while taking this joint, we have to take the least value of moment, MB value, for solving it. Okay, so that time you cannot use the standard result. If everything is uniform MB, then we can use the standard result directly. Otherwise, you have to solve it like you as usual. You have to take this MB into theta plus this MB theta plus MB theta, like that. You have to solve it. Okay. So similarly, you can solve this question. Yeah, in this question we'll have that condition. So we'll discuss that. So this is MB. This span is having different MB. Okay. So here you have any any doubt in this question? So these are the three mechanisms. Out of three, you have to choose the least value, that will be the collapse load, the least value among all. Okay, this is least.